All right, so that was some review that had to do with regression, and now we're going to move on to doing some inference for regression. So the thing that's really nice about R is that it gives you all that inferential information you want in the summary output. So if we do summary, parentheses, then the name of our model, which was M1, and control enter, everything that you need here comes from your output. So you don't have to do any hand computations. So we might want to think what our test statistic is. And in this case, our test statistic is a t-value because we use the t-distribution as our distributional approximation when we're doing inference for regression. And the value is, and then we can just read it right off of the output. So it's here in this column that says t-value, 23.27. 23.27. And if we wanted to verify that, we could always do the B1.59403 divided by 0.2553, because that's our standard error. And that's how we got that 23.27, or that's how R got it. It just divided this point estimate by the standard error. So our test statistic, our standard error is 0.0253. So those are a couple pieces of information you might need. And then the question is, what's the generic conclusion of the test? If we wanted to, we could compute the p-value ourselves, but it's just as easy to read it from this last column, which says PR for probability. So the probability of finding a t-value that is greater than the absolute value of 23.27. So on the tails, either greater than 23 or less than negative 23, that p-value, it's been computed for you by R, and it's this number right here. So we might have talked about scientific notation in R before, but let's talk about it again. So our p-value is less than 2e minus 16, which means it's less than 2 times 10 to the negative 16th. In other words, it's 0.0000016 zeros, right? 2. So it's basically 0. And in fact, that's the smallest p-value that R will ever show you, is this less than 2e minus 16. And R is also nice. It gives you these stars, which give you some indication of how significant something is. So if you have 3 stars, that basically means it's around 0. 2 stars, it's significant at the 0.001 level. 1 star, it's significant at the 0.01 level. A little period, that means it's significant at the 0.05 level, which is what we often use as our alpha cutoff. And then we've got a few more things if it's not very significant. So the p-value is basically 0. There are lots of stars in the R output because it is highly significant. So our generic conclusion is we reject the null hypothesis. And remember that our generic hypotheses when we're doing inference for a slope are that the null hypothesis is that beta 1 is equal to 0. And then our alternative hypothesis is that beta 1 is not equal to 0. So that's what we're always testing. That's what this p-value is always about. Can we reject the hypothesis that beta 1 is equal to 0? And in this case, yes, we can. That's our generic conclusion. Then the next thing that you often want to do when you're doing hypothesis testing is interpret your generic conclusion in context. And I would say we have evidence to suggest, or you could say we have strong evidence to suggest that there is a relationship between highest year of school completed by a spouse and highest year of school completed by an individual. So if we had failed to reject the null hypothesis, that would have meant our slope could just as well have been 0. We don't necessarily need a line with a slope in it in order to predict our data. But in this case, we were able to reject our null hypothesis, and that means we have evidence to suggest that there is a relationship there. The slope is different than 0. Another thing that you might want to know about is the r² value. And you can see this just by looking down in the output. It says multiple r². So in this class, we're thinking about the multiple r² value. I'm going to put $signs around it so that it gets typeset nicely as math when I knit this. And I'll put quotes. So it's the multiple r². If you took a regression analysis class, you might talk about the adjusted r², but for right now, we're just going to think about this multiple r². We're thinking about the multiple r² value, which is 0.3547. And the way that we interpret r² is the percent of the variability in the response that can be explained by the model. So we can say 35.47% of the variability in highest year of school completed by an individual can be explained by the model using highest year of school completed by a spouse as a predictor. So we can't explain all of the variability in the highest year of school someone completed, but we can explain 35.47% of the variability. Whether or not that's good kind of depends on, the context of the data. In this case, I think that's pretty good, that we could explain, we could predict someone's amount of school that they've completed using just the information about how much school their spouse completed. So this is the interpretation in context. Maybe I'll just move this up here so it's a little clearer what I'm doing. So that's the interpretation in context. And then the last thing that you might want to do when it comes to inference is do a confidence or prediction interval. So if you're following along with the textbook, this is section 9.3. And this has to do with prediction and making a better prediction rather than just a particular point estimate. So if we wanted to, we could make a prediction for a person whose spouse has completed 12 years of high school. So I have my intercept 5.85-ish plus 0.59 times the highest year of school completed of the spouse. And I could just plug this in and control enter. Okay, we would predict. So our point estimate for the prediction would be 12.97 years, so about 1 year of college. But we might want to create an interval estimate rather than just having a point estimate. We might want to be able to say, I'm 95% confident, right? So there's two different kinds of intervals that you can make. And this is one of those places where I always say statisticians shouldn't be allowed to name things because we have something called a confidence interval and then we have something called a prediction interval. And the confidence interval in section 9.3, when we're doing these intervals, we're specifically thinking about a confidence interval for a mean y, and a prediction interval is for a particular y. So we've used the term confidence interval in a generic way before, but now we're using it in a more specific way. Either kind of interval that you want to create, you use the predict function to make them. So I'm just going to show you what that code looks like. And maybe I'll put in some line breaks so it's a little bit easier to read. So I'm going to do predict and then parentheses. And then the first thing that I need to give it is a linear regression model. So I named mine M1. And then a comma. And then I need to give it some new data. And what I'm going to give it is a data.frame. And inside that data.frame, I'm going to define the value for the explanatory variable that I want to make a prediction about. So in this case, I want to make a prediction about people whose highest year of school completed of their spouse was 12. And then I'm going to put another comma, and then I'm going to say interval is equal to, in quotes, confidence. So if I control enter here, it gives me 3 numbers. It gives me a fit. And the fit is just the point estimate. So that's the same number that we just computed before. There's a little bit of rounding difference because R, when it does the prediction, is using the full decimals, but it's basically the same, 12.97 something. So that's the point estimate. And then it gives us the lower end of the confidence interval and the upper end of the confidence interval. And if I wanted to do an interval that was a prediction interval, I could do the same thing. So I've still got new data is data.frame, and I've got the interval is equal to prediction. That's the only thing that I change. And if I control enter, again, I get the interval in my console. The fit is exactly the same. So the middle of the interval is always the same. The only thing that's different is how wide the interval is. And the prediction interval is always going to be the wider interval because the prediction interval is about a particular value. So let's do interpretation for the 2 intervals. So let's start with the confidence interval. And I would say I am 95% confident that the mean of highest year of school completed for people whose spouse attended 12 years of school is between the bottom of the interval, 12.79, let's say, and 13.16, let's say, years. So I'm 95% confident that the mean is going to be between these 2 different numbers. And then for the prediction interval, this is going to be about a particular value. So I would say I am 95% confident that the number of years of school completed for a particular individual whose spouse attended 12 years of school is between, and then I'm going to pick the bottom of that interval, 8.14 and 17.91 years. So if I have to make a guess about a particular person, I'm going to give a wider interval. If I have to make a guess, I'm going to say it's between, they did 8th grade and they got all the way through college and they did some graduate school. Versus if I get to say a prediction about the mean, about a bunch of people whose spouse attended 12 years of school, that's going to balance out the people who, just went to elementary school and the people who went on to get PhDs. The mean is always going to kind of hide some of those outliers a little bit. So we can be much more confident if we're going to make a prediction about a mean than if we are about a particular person. But either way, we're putting in the spouse attended 12 years of school, spouse attended 12 years of school. So this is what makes it different than the kind of inference we were doing in section 9.1, which was just inference about a slope. Now we're doing inference about a predicted value, either the mean for that particular value or a particular value for that particular value.